Welcome to Work, Heat, and Energy. So let's begin by defining some terms that will help us in our study of thermodynamics. First, let's define the system and the surroundings. The system is the part of the universe in which we are interested, and the surroundings are everything else in the universe, everything outside the system. So we've got some system and the surroundings, we've got some boundary in between them. Now, often the system is pictured as a box, and the surroundings are outside the box. We could just as easily put the system as the outside of the box and the surroundings as the inside of the box, but it seems to make a little bit more sense for us to talk about things that are a system is enclosed in some container and the surroundings are outside that container. Now, the term open describes a system that allows matter to move into or out of the system. So that's symbolized by the top case here. We've got a blue arrow symbolizing the movement of matter. We can allow matter to move into or out of the system. And if the system is open, we also can allow energy, symbolized by this red arrow. We can allow energy to move into or out of the system. On the other hand, the term closed describes a system that does not allow matter to move into or out of the system. So there we've got a system like this, where we still allow energy to flow in and out. That's why the red arrow is pointing both directions. We can allow energy to flow into the system or out of the system, but the blue arrow is not pointing out of the system. You can see that if matter goes and strikes the wall, that it moves out of the system. Right? So in the top case, we may have, say, an open beaker, where gas is allowed to go out of the beaker or into the beaker. If we have some liquid in the beaker and that liquid evaporates, some of those molecules in the gas phase can now migrate out of the beaker. In this case, in the closed case, we have, say, a flask with a stopper on it, with no holes in the stopper. So the gas can migrate around inside the flask, but it can't move from inside the flask to outside the flask. So let's talk about the term adiabatic. This describes a boundary or a system that does not allow heat to flow into or out of the system. On the other hand, we've got diathermic, which describes a boundary or a system that allows heat to flow into or out of the system. So the terms adiabatic and diathermic are not discussing whether matter is allowed to flow into or out of the system. They're only discussing whether heat is allowed to flow into or out of the system. And the last term we need to look at is isolated. Now, this describes a system that is both closed and adiabatic. So with closed, remember, we allowed energy to flow back and forth, but we didn't allow matter to flow back and forth. With an isolated system, we're not allowing matter to flow back and forth, and we're not allowing energy to flow back and forth between the system and the surroundings. So energy is the capacity to do work. Well, that's great, but what's work? Work, which we symbolize as W, is motion against an opposing force. Now, this means that if there's no opposing force, if there's motion but no opposing force, that means that there is no work. So if you have a box sitting on a frictionless surface and you push that box, you're not doing any work, even though there was motion, because there's no motion against an opposing force. If you lift the box against gravity, now you've done some work, because now there's some force, gravity, pulling down, and you've had to do some work to oppose that force. In other words, you're giving that box some potential energy. On the other hand, heat, which is symbolized Q, is the energy that's transferred by thermal contact between two bodies. So we've got two different types of energy transfer that we're going to discuss here in thermodynamics. We can transfer energy as work, so motion against an opposing force, or we can transfer energy as heat, that thermal motion of molecules. Now, the term exothermic describes a process in which heat is released from the system to the surroundings. So the system is losing energy as heat, the surroundings are gaining energy as heat. On the other hand, endothermic describes a process in which heat is absorbed by the system from the surroundings. So the system is gaining energy as heat, and the surroundings are losing energy as heat. Now, when an exothermic process is carried out in a diathermic container, then heat flows out of the container. So that's the container we have on the right here. We've got some exothermic process. If we allow heat to flow, so we've got a diathermic barrier there, then with that exothermic process, the heat flows out of the container and the temperature remains constant. On the other hand, if we have an endothermic process like the one shown over here, then heat flows into the container to keep the temperature constant. Now, on the other hand, when an exothermic process is carried out in an adiabatic container, so now the container is insulated, the temperature of the container increases. So we've got our exothermic process over here on the right again, only now we've got some insulation around it, so we're no longer allowing heat to flow from the system out to the surroundings. And that means when that process occurs, the temperature has to increase. On the other hand, with the endothermic process, when we've insulated it, we're no longer allowing heat to flow into the system from the surroundings, and that means that the temperature of our system is going to decrease. So let's look at the molecular interpretation of heat and work. So thermal motion, from a molecular perspective, is the disorderly motion of our molecules. We've got our molecules moving around in some way, and they're moving around randomly in Brownian motion. Right? That's thermal motion of our molecules. When a system heats the surroundings, the thermal motion of the surrounding molecules increases. So if we have our system and energy is flowing out of our system as heat, then the surrounding molecules, which are up here, note that we're not picturing the molecules from the system itself, we're only picturing the molecules from the surroundings. As energy flows out of the system as heat into our surrounding molecules start moving faster, but they're all moving in different directions. They're moving in random directions, and now they're just moving in those directions faster. On the other hand, when a system is heated by the surroundings, then the thermal motion of our surrounding molecules decreases. So if energy is leaving our surrounding molecules, that basically means our surrounding molecules, when it strikes the barrier of our system, then some of that energy is transferred to the molecules in the wall, or the barrier between our surroundings and our system. And then from there, some of that thermal motion is transferred into the system. And thereby, by losing that energy to the molecule in the wall, our molecule in the surroundings has lost some of its kinetic energy. So the temperature of our surroundings has decreased slightly. In contrast, however, the motion of the surrounding molecules when work is done is orderly. So if work is done on the surroundings by the system, then all of that motion is in one direction. So if our system is, say, expanding against the surroundings, then this piston would move up. That means all of these molecules have to move the same direction. They all have to move up. Now, they're still going to retain whatever thermal motion they have. So there's still going to be some component in the, say, XY plane, but they're all going to be moving up in that Z direction. So work done by the system on the surroundings causes the surrounding molecules to move away from the system. So that was work, heat, and energy.